Let's continue. So again, so what did we do? So we first expressed our sparsest cut problem in terms of as an optimization problem for the cut metric, and the problem with that was that we can't really solve that optimization problem because it is equivalent to the original problem. Then we relaxed that condition. So instead of finding the cut metric, we said we want to find just an arbitrary metric. And that can be done using linear programming, right? So now we have this arbitrary metric that minimizes the quantity we had. So maybe scroll up. Yeah, so this is our LP, and we can solve it. So we get some arbitrary metric. We can embed it into L1 using a Bourgain embedding. And as we've seen, any L1 metric can be expressed as a combination of cuts up to scaling factor. And once we express as a combination of cuts, we can find one of those cuts, just go over all cuts, pick one of them, or we can actually just sample some cuts and pick the cut, one good cut, which gives us the solution less than this value alpha for the cut metric. So again, so once we so what happens when we now? Sorry, let me. What happens with the our LP when we embed our metric space into L1? The objective function, so the objective function sum xuv, sum over all edges uv, over sum of all pairs uv, may actually increase, right? Because some distances get distorted when we do the embedding. But in the worst case, the distances here do not change. And in here, they may decrease by a factor. At most 1 over d, so the distortion, which is decreased by a factor log n, maybe by a factor of d. So we do know that we can find an L1 metric duv. So if this is LP value originally, we can find an L1 metric with this expression duv summation over all edges, summation over all pairs divided by summation over all pairs less than LP times the distortion of our embedding, which is order of log n. Okay? Sorry? Right. So yeah, the low bound is also due to Bourgain. So if you look at just an expander graph and the shortest path, a metric on the expander graph, then it can be embedded into L1 with distortion better than log n. So that's a tight example. Now,
What do you mean when you're talking about the x with
Right. So let's compare sort of this expression. Let's compare this expression with this expression, right? So we know that the distances in the embedding do not increase. So we know that the sum of duv over all edges uv is at most the sum of distances xuv over all edges uv, right? Just for every uv, we have an equality that duv is at most xuv in the embedding we just had. On the other hand, distances uv, if you look over all pair summation, we can bound them as 1 over d summation of xuv. Upper, yeah. So we have these two bounds, right? And because of this, this expression is no more than log n times greater than this expression.
Marks you do not change because maybe it can be decreased the numerator.
Okay, yeah, in the worst case, right, okay.
Must be e in the corner.
Uh-huh.
Must be e in the corner.
Yeah, that's correct, yeah. No, what, oh yeah. So now our distribution, in general, we need many sets Z. So our construction says that the support can be very large. We can approximate this distribution. We can have actually a polynomial support Z by just sampling sufficiently many sets Z, so that's easier. In terms of L1 embedding, so it's an interesting question how many lambda s's are needed. So suppose we have some distribution on convex combination of suppose we can express duv as a convex combination of sets S. Cut matrix. So how many these sets do we need? How large can be this support? And this is a sort of actually a not so hard exercise to see that the number of or the support of this distribution, we can make it always to be n choose 2, maybe plus 1. So it's n minus 1 over 2. Anybody sees why? Why we can, so no matter, suppose somebody gives us some distribution, we can always reduce the number of lambda s in our support. So there are only relatively few non-zero guys there. And so the sort of, the answer is that you can think of this distances, right, as a n times n minus 1 over 2-dimensional vector, right? So it just tells us the distance between every pair u and v, so that duv and xs sub uv. For every uv, it's some vector telling us distances between all pairs of vertices. And of course, those vectors satisfy certain properties, but you can think of it as some high-dimensional vector. And now we are saying that some point, some vector duv, some vector d, is a convex combination of some vectors x sub s. So, and everything happens in what? It happens in n times n minus 1 over a two-dimensional space. And now we use Cauchy-Theodori theorem to argue that if a point in high-dimensional space is a convex combination of some other points, then it can also be expressed as a convex combination of, at most, n times n minus 1 over 2, probably plus 1 points, right? So in two dimension, if you have some polytope and a point inside, it can be convex combination of many points of all vertices of this polytope. We can always find 3 points, for example. Say these 3 guys. And the point is inside this triangle as well. And this is a convex combination of these 3 vertices. Okay? Any questions?
But it doesn't look like it's theoretically it exists, but how to find them? The idea was that we have to try all the vertices for being a good cut. So we need to test them.
The problem of linear programming to find such.
Yeah, but the vertices, the original number of points is exponential. So
right. No. What happens, right, is that we get this exponential number of set z, and then we can just subsample, and it's easy to show if we subsample sufficiently many samples, we'll get also a good distribution, just using very standard techniques. And when we subsample those sets z, we can find a distribution of cuts like this. And the number of cuts is also going to be a polynomial, right? Because for any choice of the set z, we only afterwards pick the threshold which we denoted by m, and there are at least maybe n distinct, at most n distinct ways to pick m with various probabilities. So we get some polynomially many cut metric z. And for cut metrics, of course, and this can of course be done afterwards using linear programming, but it's a basic solution to an LP. Okay, and so let me now then switch to the next topic, to the max cut problem.
yeah, but just last question. So still we get, even after all those improvements, we get a probabilistic algorithm.
Probabilistic algorithm, yeah.
Claim it's
Yeah, it is probabilistic. Yeah, we don't really. Yep. So, and the max cut problem is the following problem. We are given a graph G, and we would like to partition it again into pieces, but now our objective is very different from what we had before. So instead of minimizing the cut, we really want to maximize the cut. So we want to partition again it into sets S and S complement, and our goal is to maximize the number of edges going from S to S complement. We no longer have any restrictions on the sizes of sets S, so they can be small or large. I mean, they can be very small because then probably the cut isn't sufficiently large, but in principle, we don't impose any constraints on this. So we want to maximize the number of cut edges. There is this problem in some sense is much simpler than the previous problem in the sense that we can easily obtain a much better approximation. Essentially, there are many ways of getting two approximations for this problem, or half approximation. So our algorithm will be always, of course, worse than the optimal solution in this. So the value will be less than the value of the optimal solution. So two approximation or half approximation, depending on whether you divide the value of what algorithm returns to the optimal value or the other way around. The most basic algorithm is just to partition all vertices into pieces randomly. So put every vertex to the left part or right part with probability a half, and then in the expectation we will cut every edge, right, with probability a half. So every edge is cut with probability a half. So in the expectation we cut half of all edges, and since the optimal solution cannot cut all edges in the graph, more than all edges in the cut, we always get at least half approximation. This problem, so to get half approximation, we can use various other techniques. For example, the greedy algorithm will also give us half approximation. So this is really simple. But the interesting question whether we can do better, and this was an open question still mid-90s. There were many attempts to solve this problem, unsuccessful. As we've seen before, it's natural to consider a linear program for such problems. So we already know that we can try to write some metrical p. So our objective would be maybe define variables x, u, v and maximize the size of the cut. So maximize sum of x, u, v over all edges, e, and maybe add triangle inequality for x, u, v and other metric constraints. So unfortunately, this relaxation is not really good because nothing prevents this relaxation of saying that the distance between every two vertices is equal to 1. So this is really what we will get by this linear program. It will tell us that all the distances are equal to 1, and it doesn't tell us anything at all, right? So all edges are cut. And it means that it means that the integrality gap of this problem is 2, meaning that the difference between LP value can be actually larger than the optimal value, twice the optimal value.
And why can you call it integrality gap?
This is
everything is integer, just 0 and 1.
Right. So this is the integrality gap, the ratio between the LP value and the optimal LP value and the optimal value. Again, the one example is just, let's say, complete graph. In the complete graph, it's clear that we can't cut more than much more than half of all edges, and the LP can really assign 1 to every edge in the graph. So there are ways to refute this example I just showed you with the complete graph. So we can add various inequalities. For example, we can say that if you sum up distances over any triangle, that the sum is not going to be greater than 2. And this is a valid constraint for this max cut problem. But it turns out that no matter what LP constraints we add, essentially, the LP relaxation is not going to be much better. So anyway, it can give us some kind of silly solutions in some sense, and the integrality gap of essentially any LP relaxation is going to be 2. And because of this, we need more powerful technique. And this technique is called semidefinite programming, and it was introduced by Gomans and Williamson in 1994. And so what is the idea? The idea is that we kind of strengthen this LP. We will think of it of some maybe a physical model. So we want to put our graph in a maybe in a sphere and put and we assume that there are forces between vertices that push them apart. So let's put it in the graph on the sphere and see what the stable position of these vertices. So we hope that all vertices in the end will be either at one pole or another pole of that sphere. And so we'll get a perfect solution. So one set is those vertices that are in the one pole of the sphere and the other vertices that are in the other pole of the sphere. So more formally, so we will assign a vector to every vertex. So let's say our vertices are in the set 1 to n. And we have vectors v1, etc., vn corresponding to these vertices. Right? So these vectors are some vector in some high-dimensional space. And our objective is going to be maximize this distance vi minus vj squared over 4, where summation over all edges ij. Okay? And this is sort of analog of what we previously have. So this vi minus vj squared over 4 is the analog of the metric space we had before xuv in the linear program. And what's the solution we hope to get? So previously we had those cut metrics, and sort of our hope was to get a cut metric, even though after solving NLP we could get something else, and we had to use Bourgain's theorem to get a real cut metric. So here sort of the intended solution is the following. That's what we really hope to get. We have a sphere, and we have two values sort of. Think of this value as just, plus +1, and this value
Our vi should lie on the sphere or just in the Rn,
right, good. So these guys lie in the sphere. Sorry. So they're all unit factors, right? So what we really want, so if you have some solution S complement S, then we will put all vertices in S. So we'll put them to +1. So this is where vertices in S lie. And here we put vertices as the complement of S, right? And in this case, if you look at vi minus vj squared for two vertices I and j, that's what we get. If they lie in the same set, if they lie, for example, in the set S, then they're assigned the value. They both assign the value of 1, and when we look at vi minus vj squared over 4, we get a contribution of 0 in the objective function. If they lie in the S complement, then the value of both of this vi and vj is -1, and vi minus vj squared is equal to 0, right? So again, the objective function there contributes 0. Now, if they lie in the different parts of the cut, then vi minus vj is either +2 if I is an S and j is an S complement, or -2. When we square, we get 4, and we have that term of 4 because of that. So we divide by 4, we get 1. So again, for this intended solution, so if we have a cut, we can define the solution to this problem with the objective function exactly equal to the optimal solution, right? Of course, in principle, when we solve this problem, we get some other combination of vectors. So they're not going to be nice as this one. And so why do we look at this as this program? Why do we write expression like this? Particularly, why do we want really to have maybe square here? Why don't we have just, absolute value of vi minus vj? The main reason, and sort of the only reason why we look at it, is because we can efficiently solve such problems, and they're called semi-definite programming. So if we could, we would rather avoid having the square, for example. But that's just something impossible computationally. So that's because of the computational constraints. So we need to have this too. But it turns out that using semi-definite programming, this problem can be solved. And vectors in the end are going to be in some high-dimensional space. Again, we would rather prefer these vectors to lie in some low-dimensional space. But that's just not possible computationally. Yeah. Yeah, so the dimension of the space is sort of unbounded. It's in some sense infinite. But obviously, if you have n vectors, we can always embed them in n-dimensional space, right? There is a dimensional subspace that contains all these vectors. And that's why we can assume that the dimension of space n. But in general, the program itself doesn't sort of let's say if we solve this problem, we won't have any bound whatsoever on the dimension of space. And probably this is a good point to stop to today's lecture. And do you have any questions?
I didn't understand the reduction. So what do we do with our graph and with the speed? How do we place values? What is this?
Right. So we solve this maximization problem for every vertex of our graph I. We introduce a variable v sub I. This is a variable, but now it's not real valued, but it takes values in high-dimensional space Rn. And we want to maximize the following expression: summation of vi minus vj squared over 4. And it turns out that we can do this. So we solve that maximization problem subject to only one constraint, that all these vectors are unit vectors. In other words, all their lengths are equal to 1. And that's done using semi-definite programming. And maybe I'll talk a little bit more about it in the next lecture, how we actually solve this problem. And the good thing is that this is a relaxation, meaning that sort of for every optimal solution, a real solution for every cut S, there is some meaningful interpretation of that solution in terms of this SDP program. So that interpretation is that we put some vertices, assign those variables to +1 and some others to -1. So we put some vertices to one pole and some other vertices to the other pole. And of course, once we solve this SDP, we get some solution which can be very far from what we really expect. But does this answer your question, or what?
Partially, because I didn't understand how do we get the cut.
No.
Okay.
Yeah. So far I decided. I described only the program. That's sort of the first part of it. And how to find the cut, that's the main thing that Gomans and Williamson did. And this is actually very simple, but still I don't think I have any time left. So I'll start the next lecture with actually describing how to get a good cut from this. More questions?